autonomous systems such as self-driving cars continue to spread their influence into everyday lives. As engineers, it is becoming increasingly important to understand and enable design for this. To explore this topic, our objective was to design, prototype, and program a robot that could autonomously navigate and perform specific tasks. For this project, we created a robot that operates within a maze and retrieves a block without external instructions. Starting in a random position in the maze, it must identify its location, navigate to the loading zone, and retrieve a block for transport to a specified drop-off point in under 5 minutes.
From the beginning, we set strict constraints to the design, limiting ourselves to a compact circular footprint and a low center of gravity. A large portion of our initial efforts was allocated towards hardware to create a solid foundation for our software. The UFT fabrication facilities allowed us not only laser cut and drill our structure, but also to rapidly prototype various components such as the grabber mechanism and a custom ultrasonic sensor holder that allows for more accurate long-range readings. While intensive testing of ultrasonic distance sensors confirmed their accuracy in measuring distances to perpendicular surfaces, it also revealed significant performance limitations when detecting more complex geometries, such as the corners. This was particularly detrimental to its ability to both locate the block and confidently orient itself using the surrounding walls. To address these challenges, a pair of laser distance sensors proved more reliable for locating the block, and a set of 2 parallel ultrasonic sensors was used to effectively evaluate a wall profile.
The robot begins in the maze by turning on the spot until it becomes parallel to a wall, which is found when the set of 3 ultrasonic sensors on its right side read the same value. To drive forward, ultrasonic sensors on both sides provide input to a PID controller algorithm that measures the robot's distance to adjacent walls and adapts accordingly to keep it driving smoothly, quickly, and reliably through the maze. Being able to cover ground rapidly meant our robot was able to quickly determine its location by identifying unique configurations in the walls around it using ultrasonic sensors. With this, coded instructions guide it to the block loading area. Once the robot moves into the zone, it switches to laser sensors and begins turning incrementally, performing a sweep of the area until the block is found. The robot then approaches the block and picks it up, after which it reorients itself and transports the block to the specified drop-off point.
The robot continuously excelled in early performance tests, such as in basic obstacle avoidance and controlled block retrieval. And between our efforts to improve the robot, we found some time to add a little bit of artistic flair.
Make sure the audio picks that up.
Oh yeah. Oh yeah.
When it came to the final performance, the robot successfully accomplished all the tasks with an average completion time of around 2.5 minutes. Even when unplanned situations were faced, the robot adapted flawlessly. Although we managed to complete all the given tasks, there is always room for improvement. To advance this project further, the code could be written in a way that allows the robot to adapt to different maze patterns. Also, using more sophisticated processors, we could provide additional computational capacity for more intricate mazes and more complex tasks. All in all, working on this project was a ton of fun and gave us a lot of a good perspective into the world of autonomy.